Two particles, separated by any distance you can name, share something that cannot be cut, cannot be stretched, and does not weaken with space between them. Welcome to the Sleepy Lab. Tonight, we drift through one of the quietest mysteries in all of physics, the strange, unbreakable bond that can exist between two particles and what it tells us about the nature of reality itself. We will move slowly. There is no hurry here. If this kind of gentle journey through science helps you rest, consider subscribing, one sleepy soul at a time. Now, let's begin. Somewhere in a laboratory, a crystal sits in a beam of light. A single photon enters it, and two photons emerge. They travel in opposite directions, growing farther apart with every passing moment. And yet, in a way that took physicists decades to fully accept, they remain connected. Measure one of them, and you instantly know something about the other, no matter how far away it has traveled. This is quantum entanglement. It is not a metaphor. It is not a poetic way of saying two things are similar. It is a precise, measurable, experimentally confirmed feature of the physical world. Two particles become entangled when they interact in a way that leaves their quantum states mathematically inseparable. You cannot describe one without the other. They are, in a deep sense, a single system, even when the space between them is vast. Think of polarization for a moment. Light can oscillate in different directions, up and down, side to side, or at any angle in between. A photon's polarization is one of its quantum properties, and two photons can be entangled in exactly this property. When that happens, neither photon has a definite polarization on its own. They exist together in a kind of shared uncertainty. But the moment you measure one, the moment you ask it which direction it is oriented, it settles into an answer, and its distant partner settles into a corresponding answer at the same instant. Not a moment later, the same instant. The word for this, entanglement, was given to us by Erwin Schrödinger in 1935. He did not choose the word lightly. He called entanglement the defining trait of quantum mechanics, the feature that most sharply separates the quantum world from everything classical physics had built before it. Schrödinger understood that entanglement was not a curiosity at the edges of the theory, it was at the center of it. That same year, three physicists published a paper that would shape the debate for decades to come. Albert Einstein, Boris Podolsky, and Nathan Rosen, their initials giving the paper its name. The EPR paper looked at entanglement and felt deeply uneasy. Their argument was careful and serious. If measuring one particle instantly constrains the outcome of a measurement on another, far-away particle, then either something is traveling between them faster than light, or the particles somehow knew their answers in advance. Einstein found both possibilities troubling. The first would violate everything he had built in relativity. The second suggested that quantum mechanics was simply incomplete, that there were hidden facts about the particles, pre-existing values that the theory was failing to account for. He had a phrase for the alternative, for the idea that one particle could somehow reach across space and influence another instantaneously. Spooky action at a distance. He said it with skepticism, almost with distaste. His conviction was firm. No physical influence should act instantaneously across space. The universe, he believed, was local. A particle here could not be affected by something happening over there, right now, with nothing traveling between them. And so the EPR paper proposed a way out. Perhaps the particles carry hidden variables, something like preset instructions, written into them at the moment they were created. Instructions that would determine their measurement outcomes in advance, without any need for mysterious long-range influence. It was a reasonable idea. It was also, as it turned out, wrong. But that conclusion would take time to arrive. For nearly 30 years after the EPR paper, the question remained philosophical. There was no experiment that could settle it. No way to reach into the mathematics and ask the universe directly which picture was true. The particles kept their secret a little longer. And in the quiet of those decades, the debate lived mostly in letters and conversations between physicists who cared deeply about what the theory actually meant, not just what it predicted, but what it said about the nature of reality. Einstein never stopped believing that quantum mechanics was incomplete. He never accepted that the universe could be genuinely non-local, that two distant particles could share a bond with no thread connecting them, no signal passing between them, no hidden instruction guiding them. He died in 1955, still holding that conviction. The experiment that would have changed his mind had not yet been designed. What we know now, and we will explore this more deeply as the night continues, is that the correlations between entangled particles are real, and they are stronger than any hidden instruction set could produce. The universe does not hide pre-written answers inside its particles. The outcomes are genuinely undetermined until the moment of measurement, and yet, when two entangled particles are measured, their outcomes agree in ways that cannot be explained by anything traveling between them, and cannot be explained by anything they carried from the start. This is not a gap in our understanding. It is not a place where we simply haven't looked hard enough yet. It is a confirmed feature of how the world works, tested in laboratories across many decades by many independent teams, with results that have held every time. And yet, and this is the part that takes a moment to settle, none of this allows a message to travel faster than light. Knowing that your particle gave one answer tells you what the distant particle gave, but you had no control over which answer your particle chose. You cannot use that to send information. You cannot encode a message in a correlation you cannot steer. The universe is strange, but it is consistent. Entanglement connects without communicating. It correlates without signaling. It is a bond that crosses distance without crossing it in any way that physics forbids. Einstein called it spooky. Perhaps the quieter word is simply deep. Two particles, born together in a moment of interaction, carrying a shared quantum state out into the world, growing apart and remaining, in some sense that our ordinary language struggles to hold together. The mathematics does not struggle. The mathematics is perfectly clear. It is only we, lying here in the dark, trying to picture it, who feel the strangeness settle over us like something we almost understand. And that feeling, that soft edge of almost, is a good place to rest. So we rest there for a moment, in that soft place where the strangeness has settled, but the questions have not quite dissolved. Because there is more to this story, and it moves slowly, the way good things do. When Einstein, Podolsky, and Rosen wrote their paper in 1935, they were not trying to dismiss quantum mechanics. They respected it too much for that. What they were trying to do was something more careful. They were trying to show that it must be incomplete. Their argument went something like this. If two particles, separated by a great distance, always give correlated answers when measured, then either something travels between them at the moment of measurement, which Einstein found deeply troubling, or the answers were already decided, long before anyone asked. The second option felt more reasonable to them, more orderly, more like the universe they believed in. Perhaps each particle, when it was created, was given a set of instructions, a quiet list written into its nature, telling it exactly what to say when asked about its spin, its polarization, its state. The particles would carry these instructions with them as they traveled apart, And when the measurements came, they would simply follow the list. No mystery, no spooky action, just information, packed in advance, like letters sealed before the journey. These were called hidden variables. Hidden not because they were secret, but because quantum mechanics, as written, did not account for them. They were the missing pages. Einstein believed that would one day make the theory whole. And for a long time, nearly 30 years, no one could say with certainty whether he was right. The debate lived in the realm of philosophy, of interpretation, of what you believed the mathematics was really saying. Physicists would argue at conferences, in letters, over long dinners, and then go home without resolution, because there was no experiment that could settle it. The two pictures, hidden variables on one side, genuine quantum non-locality on the other, made the same predictions, or so it seemed. That is a strange place for science to be. A question that feels real, that matters deeply, but cannot yet be touched by measurement. It sat there, patient and unresolved, through the 1940s, the 50s, into the early 60s. And then, in 1964, a physicist named John Bell did something quiet and extraordinary. He sat down and worked through the mathematics very carefully. He asked, if particles really do carry hidden instructions, if their outcomes are predetermined by some list we cannot see, then how correlated can their answers possibly be? And he found a ceiling. Not a physical ceiling, not a technological one, a mathematical one. A hard limit on how strongly two separated measurements can agree. If the world is locally realistic, if each particle carries only its own information, and nothing travels between them at the moment of measurement. He expressed this as an inequality, a precise numerical bound. If you run the experiment many times, measuring pairs of particles at various angles, and you calculate a certain combination of those correlations, a locally realistic theory says the result cannot exceed a particular value. It is bounded. It is capped. Bell's inequality is not complicated to state, though it takes care to derive. It simply says, if the world works the way Einstein hoped, the correlations between distant measurements can only go so far. And then Bell noted something else. Quantum mechanics predicts that entangled particles will violate that bound, that their correlations will be stronger than any hidden instruction set could produce, that the ceiling Bell had calculated would not hold. This was the key. For the first time, the two pictures made different predictions, not just philosophically different, numerically different, measurably different. The question had finally come down from the realm of interpretation and landed, quietly, in a laboratory. It took 8 years for someone to test it. In 1972, a physicist named John Clauser, working with colleagues at Berkeley, built an apparatus using calcium atoms. When those atoms were excited and then relaxed, they released pairs of photons that emerged entangled in their polarization. Clauser and his team measured those photons at different angles, again and again, accumulating the statistics Bell's test required. The experiment was painstaking. The equipment was delicate. The photons were faint, but the results came through. The correlations exceeded Bell's bound. Not by a little, not within the margin of error. The entangled photons were more correlated than any pre-shared classical instruction set could have made them. The hidden variable picture, at least in its simplest, locally realistic form, could not explain what the detectors were recording. It was a careful result, and Clauser was careful about it. There were still loopholes, ways a determined skeptic could argue the experiment had not fully closed the case. Perhaps the detectors were not efficient enough. Perhaps the settings were chosen in a way that left some subtle opening. These were not unreasonable concerns. Science moves slowly when the stakes are this deep. But the direction was clear. The universe, it seemed, was not using hidden instructions. The particles were not carrying a list. The correlations were real, and they were stronger than local realism allowed. Einstein's hope that the world was orderly in that particular way, that the spookiness was only apparent, a gap in our knowledge rather than a feature of nature, that hope was beginning, gently, to close. And yet the closing was not dramatic. It happened in papers, in careful language, in numbers that exceeded a mathematical bound by a measured amount. It happened the way most true things happen in science, slowly, incrementally, with each experiment tightening the case a little further. There is something worth sitting with in that. 30 years of philosophical debate, and then a single inequality, derived by one person working quietly through the logic. And suddenly, the question had a shape that experiments could reach. Bell did not live to receive the Nobel Prize that his work eventually helped earn. He died in 1990, before the full weight of what he had done was widely recognized. The prize came in 2022, awarded to Clauser and two others whose work we will come to in a moment. But Bell's inequality was the hinge, the place where an ancient argument about the nature of reality became, at last, a matter of measurement. And measurement said, the particles are not following a list, they're doing something else, something that our ordinary picture of the world, where things have definite properties, where influences travel through space, where what happens here does not instantly constrain what happens there, cannot fully contain. The correlations are real. They are stronger than they should be, if the world were locally realistic. And they appear, as far as every careful experiment has shown, every single time. Not because a signal travels, not because the particles communicate, but because they share something that is not quite a property, not quite a message, not quite anything our everyday language has a word for. A quantum state held jointly, indivisible, persisting across whatever distance separates them. Bell gave us the ruler to measure the strangeness, and the strangeness measured true. So we lie here in the quiet and we let that settle. A question that lived for 30 years without an answer, and then an answer that arrived not with noise, but with numbers, with photons from calcium atoms, counted patiently in a laboratory in 1972. The universe does not always announce its secrets. Sometimes it simply lets them be measured. And yet the measurements in 1972 were not quite the end of the story. There were gaps, small ones, but real, places where a skeptic could still stand and say, perhaps there is another explanation. Perhaps the experiment itself is leaving a door open. One of those doors had a name, the locality loophole. It worked like this. In Clauser's original experiment, the detector settings, the angles at which the polarizations were measured, were chosen before the photons left the source. A hidden variable theory, if it were clever enough, might imagine that the photons somehow knew in advance which settings they would encounter, that they carried, not a full set of instructions, but just enough information to fool that particular arrangement. It sounds unlikely, and it probably is, but science does not close doors by saying something sounds unlikely. It closes them with experiments. So, in 1982, a physicist named Alain Aspect, working in Paris, did something more careful. He waited until the photons were already in flight, and then he switched the detector settings. The photons had already left the source. They were already traveling toward their respective detectors, and only after they were airborne, so to speak, did the experiment decide how it would measure them. There was no longer any moment at which the photons could have known what was coming, no window in which a hidden variable could have been briefed. And still, the correlations held. Still, Bell's inequality was violated. The universe did not seem to care that aspect had changed the rules mid-flight. The entangled pairs continued to behave as though they shared something that no distance and no last-minute adjustment could sever. Aspect's experiment did not silence every objection. Science rarely works that way. There was still the detection loophole, the fact that not every photon in the experiment was actually detected, and one could, with some effort, imagine that the detected ones were a special, non-representative sample. A skeptic could argue that the photons being counted were the cooperative ones, and the rest, undetected, might have told a different story. It was a thin argument, but it was an argument. And so the work continued. For decades, experimenters refined their tools, better detectors, more efficient sources, more precise timing. Each experiment closed a little more of the remaining space. Then, in 2015, a team led by Bas Hinsen in Delft, the Netherlands, ran an experiment that closed both loopholes at once: the detection loophole and the locality loophole, simultaneously in a single, carefully designed test. They used not photons, but electrons, held in diamond crystals, separated by about 1.3 kilometers. The detection efficiency was high enough to close the detection loophole. The measurements were space-like, separated, meaning the two measurement events were so far apart in space and so close together in time that not even light could have carried information from one to the other before both measurements were complete. The result was the same. Bell's inequality violated. Local realism ruled out, not with a loophole remaining, but cleanly, with both doors closed at once. It had taken 43 years from Bell's paper to that moment. 43 years of careful, patient, sometimes painstaking experimental work. And at the end of it, the answer was the same answer the universe had been quietly giving all along. The correlations are real. They're not a trick of the apparatus. They're not a sampling artifact. They're not a consequence of pre-shared instructions. They're something the world actually does. In 2022, the Nobel Committee in Stockholm recognized what those decades of work had established. John Clauser, Elaine Aspect, and Anton Zeilinger shared the Nobel Prize in Physics. 3 experimenters across 3 generations of the same question, each one building on what the last had left open, each one pressing a little closer to certainty. It is a quiet kind of honor, in a way, a prize for showing that something strange is true, for refusing to let the strangeness be explained away. And now, lying here in the dark, you might find a question forming at the edge of thought. If the correlations are real, if measuring one particle truly constrains what the other will yield, no matter how far away it is, then why can't we use that to send a message? Why can't we use entanglement to communicate faster than light? It is a natural thing to wonder, and the answer is one of the more quietly beautiful constraints in all of physics. You cannot control what outcome your particle produces. That is the heart of it. When you measure your half of an entangled pair, you get a result, but you do not choose the result. The outcome is random, genuinely, irreducibly random, as far as any experiment has ever shown. You might measure spin up, or you might measure spin down, and there is no lever you can pull to decide which one you get. Your distant partner's particle will be correlated with yours, but they also cannot predict what they will find until they measure it. And when they do measure it, they see a random result too. It is only when the two of you later compare notes through an ordinary, classical channel at ordinary, classical speeds that the correlation becomes visible. The correlation lives in the comparison, and the comparison requires a classical message which cannot travel faster than light. This is not a loophole or a limitation waiting to be engineered around. It is a theorem. The no communication theorem, as it is called, proves mathematically that no manipulation of an entangled system on one side can produce any detectable change in the statistics on the other side. The randomness is precisely what seals the channel. The universe arranged things so that the non-locality is real and the correlations are real, and yet no information rides on them. Einstein's worry that entanglement would allow instantaneous influence across space turns out to be both confirmed and diffused at once. The influence, if we want to call it that, is real, but it carries nothing. It cannot be aimed or loaded or read. It simply is. And so we arrive at something that took physicists decades to fully absorb. Entanglement is not a curiosity. It is not a philosophical puzzle to be set aside once the equations are written down. It is a resource. A physical resource, as real as energy or mass. Something that can be created in a laboratory, in a crystal, or between trapped ions held in a magnetic field. Something that can be stored, carefully, in systems shielded from the environment. Something that can be distributed, sent down a fiber, or beamed through open air, or relayed through a satellite to a distant location. And something that can be consumed, used up in a single act of measurement to accomplish a task that classical physics cannot. Quantum cryptography, quantum computing, quantum sensing, quantum networks that may one day connect distant processors the way copper wire once connected distant cities. All of these rest, at their foundation, on entanglement as a resource that can be handled, husbanded, and spent. The strange thing that Einstein called spooky, the thing that Schrödinger named and worried over, the thing that Bell made measurable and Clauser and Aspect and Zeilinger spent their careers confirming, has become, in the hands of engineers and experimenters, something almost practical, almost ordinary, in the way that electricity once seemed extraordinary and now simply hums behind the walls. Not quite ordinary yet. We are still early in learning how to hold it, how to move it, how to keep it from dissolving back into the noise of the world. But the foundation is there, tested, confirmed, and understood well enough to build upon. And somewhere tonight, in a laboratory that is probably very quiet, a crystal is splitting photons into pairs, and two particles are beginning their brief, correlated lives, carrying between them something the universe permits, and our language still struggles to name. And so we find ourselves here, at the edge of something that requires a little more care to see clearly. The crystal splitting photons is a good place to begin, but to understand what it is actually doing, it helps to go back one step further, to the nature of the particles themselves before they are ever paired. A single particle, a photon, an electron, an atom, does not always have a definite value for its properties before it is measured. This is not a limitation of our instruments. It is not that the particle has a hidden answer we simply cannot read. As far as the mathematics can tell us, and as far as experiment has confirmed, the particle exists in a superposition, a kind of weighted blend of possibilities, all present at once, none of them yet settled. A photon traveling through space may have no definite polarization. It is not secretly horizontal, waiting to be discovered. It holds both possibilities, and all the angles between them, in a kind of suspended coexistence until something interacts with it, until a measurement is made. And then, in that moment, one outcome emerges. The others do not linger. This is one of the quieter strangeness of quantum mechanics, not the entanglement itself, but the ground it grows from. The fact that the world, at its smallest scales, does not commit until it must. Now take two such particles. If they interact in the right way, their superpositions do not remain separate. They become linked, mathematically woven together into a single description. And this is where something genuinely new enters the picture. When two particles are entangled, their joint quantum state cannot be written as a product of two independent states. You cannot say, this particle is in this condition, and that particle is in that condition, and together they make a pair. The mathematics does not allow it. The two descriptions have merged into one, and that one description belongs to neither particle alone. Physicists sometimes say the pair shares a single quantum state, and that phrase, though it sounds almost poetic, is meant quite literally. There is one wave function, one mathematical object, and it stretches across both particles regardless of where they are. This is what makes entanglement different from ordinary correlation. Two gloves in separate boxes are correlated. Find a left glove in one box, and you know the other is right. But each glove always was what it was. The correlation was written in from the beginning. The gloves had their handedness before you opened either box. Entangled particles are not like that. Before measurement, neither particle has a definite value for the property being measured. The outcomes are genuinely undetermined, not hidden, not pre-assigned, not waiting in some sealed envelope. Bell's theorem, and the decades of experiments that followed it, have made this as clear as anything in physics can be made. The correlations that entangled particles produce are stronger than any pre-shared classical instruction set could generate, stronger than any arrangement of hidden variables could explain. And yet, when you measure one particle, the other, wherever it is, will yield a correlated result. It is worth sitting with that for a moment. Not because it should alarm you, but because it is genuinely one of the more remarkable things the universe does quietly, without announcement, in laboratories and in nature, all the time. Measuring one particle does not send a signal to the other. This is important, and it is sometimes misunderstood. The measurement does not reach across space and tap the second particle on the shoulder. It does not transmit anything. What it does is reveal a correlation that was encoded in the shared quantum state, a correlation that had no definite value before, but which, once one side is measured, constrains what the other side can yield. The correlation is real. The non-locality is real. The signal is absent. These three things coexist, and the mathematics holds them together without contradiction, even if our intuitions find the combination uncomfortable. Now, the crystal. One of the most common ways to create entangled photon pairs in a laboratory is a process called spontaneous parametric down conversion. The name is long, but the idea has a certain elegance to it. A single photon enters a carefully chosen crystal, a non-linear optical material, the kind whose internal structure responds to light in ways that ordinary glass does not. And inside that crystal, something unusual can happen. The photon, with some small probability, ceases to exist as a single photon, and in its place, two new photons emerge. Each of these new photons carries roughly half the energy of the original. Their frequencies are lower, their wavelengths longer, and together, they conserve the energy and momentum that the original photon carried in. The crystal does not create energy from nothing. It redistributes what was already there. But the remarkable part is not the splitting itself. It is that the two photons emerge without definite individual polarizations. Their polarizations are not assigned at the moment of creation. They are left in a superposition, jointly described, mathematically inseparable. They are entangled. The crystal must be oriented with great care, a process called phase matching. so that the conditions for energy and momentum conservation are met precisely. When this is done correctly, the two photons emerge in two spreading cones of light. And at the points where those cones intersect, the entanglement is strongest, the correlations most reliable. These intersection points are where experimenters place their optical fibers, their beam splitters, their detectors, collecting the pairs as they emerge, routing them toward whatever measurement or task the experiment requires. It is a quiet process. The crystal sits in its mount. The pump laser sends photons in, and occasionally, not always, a pair comes out the other side, carrying between them the shared quantum state that no classical object can replicate. Spontaneous parametric down-conversion has become one of the workhorses of quantum optics. It is how many of the Bell test experiments generated their entangled pairs. It is how quantum cryptography systems produce their correlated photons. It is how researchers in dozens of laboratories around the world on any given night are generating the raw material of quantum information. A single photon goes in, two come out, and the universe, in that small transaction, has done something that took humanity most of the 20th century to understand. There is something almost meditative about it. The repetition, the quiet, the small scale of it all. A crystal no larger than a fingertip, a beam of light, and pairs of photons drifting outward, each one carrying half of a description that belongs to neither of them alone. The mathematics that governs this is precise and well tested. The experiments that confirm it have been refined over 50 years. And still, when you follow the logic all the way to its end, two particles, no definite properties, one shared state, correlated outcomes across any distance, the picture that emerges is one that sits just at the edge of what ordinary language can hold. Not beyond understanding, but beyond the kind of understanding that fits comfortably into everyday intuition. And perhaps that is all right. The universe is not obligated to be intuitive. It is only obligated to be consistent. And in this, at least, it has not disappointed. The crystal itself is worth pausing on for a moment. It is not simply a passive vessel through which light passes. It is a precisely engineered structure, chosen and oriented so that the physics of the splitting works out exactly right. The process has a name, phase matching, and it refers to a requirement that the universe imposes on any such transaction. Energy must be conserved. Momentum must be conserved. The incoming photon and the two outgoing photons must balance the way a careful equation balances on both sides. If the crystal is not oriented correctly, the splitting simply does not happen with any reliability. The geometry of the material, the angle of the incoming beam, the temperature of the crystal itself, all of it must be tuned with quiet precision. This is one of the places where the strangeness of quantum mechanics meets the very ordinary demands of bookkeeping. The universe keeps careful accounts. Nothing is created from nothing. Even in this small act of splitting light, the ledger must close. And when it does close, when the conditions are right, something emerges from the crystal that is worth picturing slowly. The two photons do not simply scatter in random directions. They emerge in cones. Two cones of light, spreading outward from the crystal like the opening of two soft bells. And where those cones intersect, at the edges, where the geometry of one overlaps with the geometry of the other, that is where the entanglement is strongest. That is where the pairs are found. One photon in each cone, their shared state intact, their connection already woven into the fabric of what they are. It is a strangely beautiful image, if you let yourself rest in it. Two cones of light, a narrow crystal, and at the places where the light overlaps, something that has no classical equivalent quietly waiting to be used. The polarization of those photons is worth understanding. because it is one of the clearest windows into what entanglement actually means. Polarization is a property of light, a direction, in a sense that describes how the electric field of the photon is oriented as it travels. Horizontal, vertical, diagonal. These are the possibilities. And for an ordinary photon, polarization is a definite thing. It has one. But for an entangled photon, half of a pair produced in that crystal, the polarization is not definite. Not because we do not know it, but because, as far as the mathematics is concerned, it does not yet have one. It exists in a superposition of possibilities, neither horizontal nor vertical, neither one thing nor another. And yet, when you measure it, when you force it to declare itself, something happens to its partner, wherever that partner may be. The partner's polarization is not independent, it is anti-correlated. If one photon is found to be horizontally polarized, the other will be found to be vertical. Every time. Not sometimes. Every time. This is not a coincidence. It is not a matter of the photons having secretly agreed on their answers before they left the crystal. Bell's theorem, and the experiments that followed it, ruled that out long ago. The outcomes are genuinely undetermined until the moment of measurement, and yet they are perfectly coordinated across whatever distance separates them. There is no comfortable way to hold that picture. It is simply what the experiments show. And it is worth knowing that photons are not the only place this happens. Entanglement is not a special property of light. It is a property of quantum systems in general, and it has been coaxed into existence in a remarkable range of physical settings. Atoms can be entangled, individual ions, atoms stripped of one or more electrons, held in place by carefully shaped electromagnetic fields, can be entangled with one another, their internal energy states linked in the same way that photon polarizations are linked. Superconducting circuits, cooled to temperatures close to absolute zero, can carry entangled quantum states in the form of tiny oscillating currents. Even mechanical oscillators, small physical objects that vibrate, have been brought into entangled states in laboratory settings, their motion correlated in ways that have no classical explanation. The universe, it seems, does not restrict this behavior to any particular kind of matter. Wherever quantum mechanics holds, and as far as we can tell, it holds everywhere, entanglement is available as a possibility. Each of these physical systems has its own character, its own strengths and limitations. Photons travel easily and quickly, which makes them natural carriers of entanglement across distances. But they are difficult to hold still, difficult to store. They move at the speed of light, and that is not always convenient when you need to keep a quantum state intact for a while. Ions are different. A trapped ion, suspended in a vacuum by electromagnetic fields, can hold its quantum state for a remarkably long time, seconds, in some experiments, which may not sound like much, but in the world of quantum information, where decoherence is always pressing in from the edges, seconds is a long time. Long enough to perform operations, long enough to use the entanglement for something before it dissolves back into the ordinary noise of the world. This is why trapped ion systems have become one of the leading platforms for quantum memory experiments. The attempt to store quantum information, not just process it in the moment, but hold it, preserve it, retrieve it later. The ion sits quietly in its trap, its internal state encoding something, its entanglement with a distant partner still intact, waiting. There is something almost restful about that image. A single ion, suspended in silence, holding a quantum state the way a still pool holds a reflection. But not every entangled state is equally well made. This is where the idea of fidelity comes in. Fidelity, in this context, is a measure of how closely a produced entangled state matches the ideal, the theoretical state that the mathematics describes as perfect. A fidelity of 1 means the state is exactly what it should be. The correlations are as strong as they can be. The quantum information is intact. Nothing has been lost to noise or imperfection in the preparation. A fidelity below 1 means something has gone slightly wrong. The state is entangled, perhaps, but not as purely as intended. The correlations are there, but softened. The quantum information is present, but partially blurred. In practice, fidelity is always somewhat below 1. The crystal is not perfect. The detectors introduce small errors. The alignment drifts. The environment is never entirely quiet. Every real experiment is a negotiation between the ideal and the achievable, and fidelity is the number that tells you how well that negotiation went. Researchers working on quantum systems spend a great deal of their time chasing fidelity, improving it by fractions, identifying the sources of loss and addressing them one by one. It is patient, careful work, the kind that does not announce itself loudly but accumulates slowly into something reliable. And this, perhaps, is the texture of the field as a whole. Not dramatic revelations arriving all at once, but a quiet, steady refinement. A crystal aligned a little more precisely, a trap made a little more stable, a measurement a little less noisy than the one before. The physics at the heart of it remains strange. The entanglement remains something that ordinary language struggles to hold. But the work of understanding it, of building with it, of testing it against the world, that work has a rhythm to it that is almost ordinary, almost calm. And so the work continues, not in grand leaps, but in the slow accumulation of small improvements, each one barely visible on its own, each one mattering enormously in the end. But there is something working against all of it, something that does not announce itself, does not arrive with force, but is always present, always waiting at the edges of every carefully prepared system. It is called decoherence, and it is, in a quiet way, the central difficulty of the entire field. When a particle holds a quantum state, a superposition, an entanglement, it holds something extraordinarily delicate. The state exists not because the particle is isolated from the world, but in spite of the fact that it is not, the world is always pressing in. Vibrations in the surrounding material, fluctuations in temperature, stray electromagnetic fields drifting through the apparatus, light that was not supposed to be there. Any of these can reach the system. And when they do, something happens that is almost the reverse of what the experimenters are trying to achieve. The entanglement does not simply weaken. It does not fade like a color left in sunlight. What happens is more specific than that. The quantum system becomes entangled with the environment instead. The delicate correlation that was carefully prepared between two particles begins to spread outward, leaking into the surrounding world, becoming shared with so many degrees of freedom that it can no longer be recovered or used. The entanglement is not destroyed. Exactly. It is diluted beyond reach. And the threshold for this is remarkably low. A single photon, one stray particle of light, arriving uninvited, brushing against the system for a moment too brief to measure in ordinary terms. That is enough. That single interaction can be sufficient to unravel what took enormous care to build, because the photon carries information away with it. It becomes entangled with the system, and in doing so, it pulls the system into a relationship with the wider environment. The original entanglement between the two prepared particles is compromised. The fidelity drops. The correlation weakens. This is why quantum systems are kept cold, often colder than anything that occurs naturally in the universe. near absolute zero, where thermal vibrations slow almost to stillness. This is why they are shielded, isolated, placed inside chambers designed to exclude as much of the ordinary world as possible. The environment is the adversary, not a hostile one, simply an indifferent one. The universe does not care about the experiment. It goes on doing what it does. And what it does is interact, and interaction is precisely what entanglement cannot survive for long. And yet, there is a way to fight back. Not by eliminating decoherence entirely, that remains beyond reach, but by building systems that can tolerate it. Systems that can detect when something has gone wrong and correct it before the damage spreads too far. These are called quantum error correction codes. The idea is subtle and worth sitting with for a moment. In classical computing, protecting information is relatively straightforward. You can simply copy it, store the same data in 3 places, and if one copy is corrupted, the other 2 can vote on what the correct value should be. Simple, reliable, effective. But in quantum mechanics, copying is forbidden. There is a theorem, the no-cloning theorem, that proves it is impossible to make a perfect copy of an unknown quantum state. The very act of copying would require measuring the state, and measuring it would collapse it. The copy would not be a copy of what was there before measurement, but of what measurement forced it to become. So quantum error correction takes a different approach. Instead of copying a single qubit, it encodes the logical information across multiple physical qubits. The information is spread out, distributed, hidden in the relationships between particles rather than stored in any one of them. If decoherence disturbs one of the physical qubits, the logical information survives in the others. And by measuring the relationships between qubits, not the qubits themselves, it is possible to detect that something went wrong and apply a correction without ever directly observing the protected state. It is a remarkable piece of mathematics, a way of using entanglement to protect entanglement. The very phenomenon that makes quantum systems fragile is also, when carefully arranged, what makes them resilient. The codes are not perfect. They require overhead, many physical qubits to protect a single logical one, and they require that the error rate in the underlying hardware stay below a certain threshold. But they represent a genuine path forward, a way of building quantum systems that can operate long enough to be useful, even in a world that is always trying to disturb them. And if entanglement can be protected, then it can also be moved. This is where something called entanglement swapping becomes important. Consider 2 particles. Call them A and B. They have never interacted. They are separated by a great distance, and there is no direct path between them. Under ordinary circumstances, they would have no quantum relationship at all. But now introduce 2 more particles, C and D. Particle C is entangled with A. Particle D is entangled with B. C and D are brought together and measured in a particular way, a joint measurement that does not reveal their individual states, but instead projects them into an entangled relationship with each other. Something unexpected follows. A and B, the 2 particles that never met, never interacted, never shared any history, are now entangled with each other. The entanglement has been transferred, swapped through the intermediary pair. The connection that existed between C and A and between D and B has been rerouted into a connection between A and B directly. This is not a trick of language or a loose analogy. It is a real physical effect, demonstrated in laboratories, reproducible, measurable. 2 particles can share a quantum state without ever having been in the same place. And this has a practical consequence that reaches far beyond the laboratory. Entanglement cannot travel indefinitely through optical fiber. The photons that carry it are absorbed and scattered as they go, over distances of more than roughly 100 kilometers. The signal becomes too weak, the fidelity too low, the entanglement too degraded to be useful. Classical networks solve this with repeaters, devices that receive a signal, amplify it, and send it on. But quantum states cannot be amplified without being measured, and measuring them destroys what they carry. Entanglement swapping offers a different solution. A quantum repeater does not amplify, it swaps. Entanglement is established over a short segment, then over the next segment, then the two segments are connected through a swapping operation, extending the entanglement further. Segment by segment, the connection grows until two nodes separated by a vast distance share an entangled pair that neither could have reached directly. The process is slow. It requires quantum memory, the ability to hold an entangled state while waiting for the neighboring segment to succeed, and it requires that the fidelity at each step remain high enough that the final result is still useful. But it is, in principle, a way of building a quantum network that spans not just a room or a building, but a city, a continent, eventually perhaps more. And once two distant particles are entangled, something else becomes possible. Something that sounds, at first, like it belongs to a different kind of story entirely. It is called quantum teleportation. Not the teleportation of science fiction. Nothing physical moves. No matter is disassembled and reassembled somewhere else. What is transferred is something more abstract and, in its own way, more profound. It is the quantum state itself. The complete description of a particle, its superposition, its phase, every quantum property it holds, can be transferred to a distant particle, using an entangled pair as the channel. The original particle does not travel. The information about its state does not travel through the fiber as a classical signal. And yet, at the far end, a particle emerges holding exactly the state the original held. The original state is gone from where it started. It has arrived somewhere else, carried not by any physical medium, but by the quiet, distance indifferent connection that entanglement provides. There is one small detail worth holding before we let teleportation settle into the background. The transfer cannot happen faster than light. Not because entanglement is slow. It is not slow in any ordinary sense, but because completing the teleportation requires a second channel, a classical one, an ordinary message sent through ordinary means, carrying a small piece of information that tells the receiving particle how to interpret what it has received. Without that message, the distant particle holds something, but it does not yet know what. The entanglement provides the channel. The classical signal provides the key, and a classical signal cannot outrun light. So the universe's speed limit holds, quietly, firmly, as it always does. The first time this was demonstrated in a laboratory was in 1997. A group of physicists in Innsbruck, working under Anton Zeilinger, transferred the quantum state of a photon to another photon across a small but real distance. The original photon state was gone. The receiving photon held it instead, exactly as the mathematics had predicted. It was not a large distance. It was not a dramatic demonstration in the way that word is sometimes used. It was careful, precise, and patient work. The kind of work that tends to matter most in the long run. And it opens something. Not just a technique, a direction. If quantum states can be transferred, if entanglement can be distributed across fiber and through air and eventually through space, then the question becomes not only what can be computed or communicated, but what can be protected. Because information, in the end, is only as useful as it is secure. There is a way of using entanglement and the deep strangeness of quantum measurement to build a kind of security that does not depend on the difficulty of a mathematical problem. It depends instead on the laws of physics themselves. It is called quantum key distribution. The idea is this: two parties wish to share a secret key, a string of random bits they can use to encrypt a message. They do not want anyone else to learn that key. In the classical world, the security of such an exchange rests on assumptions, on the belief that certain calculations are too hard to reverse. But those assumptions can, in principle, be broken, given enough time or a powerful enough machine. Quantum key distribution offers something different. One of the earliest protocols, known as BB84, uses individual photons sent in carefully chosen polarization states. The receiver measures each photon, and through a process of comparing a subset of their results over a public channel, the two parties can distill a shared secret key. The security does not come from mathematical hardness. It comes from the fact that a quantum state cannot be copied without disturbing it. This is not a design choice. It is a consequence of quantum mechanics itself. A principle called the no-cloning theorem, which holds that it is impossible to make a perfect copy of an unknown quantum state. An eavesdropper who intercepts a photon must measure it, and measuring it changes it. The disturbance shows up as errors in the key, errors that the two parties can detect. If the error rate is low enough, the channel is clean. If it rises above a certain threshold, something is wrong. Someone may be listening. The key is either secure or it is known to be compromised. There is no silent interception. A later protocol, developed by Arthur Eckert in 1991, takes this further. It uses entangled photon pairs directly, and it ties the security guarantee to something we have already spent time with tonight: Bell's inequality. If the two parties measure their entangled photons and find that the correlations violate Bell's inequality by the expected amount, they know the particles have not been tampered with. Because any eavesdropper who intercepts and measures a photon necessarily entangles themselves with the system, and that entanglement with a third party reduces the correlations between the original two. The Bell violation weakens, and the weakness is detectable. Security, in this framework, is not assumed. It is measured. There is something quietly remarkable about that. The same experimental tests that confirmed the non-locality of quantum mechanics in the 1970s and 1980s, the same Bell inequalities that Clauser and Aspect worked so carefully to probe, turn out to be the very tool that guarantees a cryptographic key is uncompromised. The physics and the security are the same thing. But quantum key distribution, as powerful as it is, faces a practical challenge. Photons traveling through optical fiber lose intensity over distance. The quantum states they carry are fragile. Decoherence, absorption, scattering, all of these erode the signal. Over distances of more than a few hundred kilometers, the error rate climbs too high for a usable key. Quantum repeaters can help, but they are still maturing as a technology. There is another path, though, one that bypasses the fiber entirely. Space. Above the atmosphere, there is no glass to absorb a photon, no impurities to scatter it. A photon traveling through the vacuum of space can cover enormous distances while remaining coherent. And if a satellite could distribute entangled photon pairs to two ground stations far apart, those stations could share a quantum key across a distance no fiber link could currently bridge. In 2017, a Chinese satellite called Mikius did exactly this. It carried a source of entangled photon pairs, and it distributed those pairs to two ground stations in China, separated by more than 1,200 kilometers. The entanglement survived the journey. The Bell inequality was violated at the expected level. The correlations held. across a distance that would have seemed implausible to the physicists who first debated these ideas in 1935. The satellite had to compensate for a great deal. The atmosphere bends and scatters light. The satellite moves, introducing a Doppler shift in the photon's frequencies. The ground stations must track the satellite precisely, catching photons that arrive in narrow windows as it passes overhead. The engineering required to make this work is, in its own way, as intricate as the physics. And yet it worked. 1,200 kilometers, 2 ground stations, 1 entangled pair, shared between them. A quiet demonstration that the infrastructure of a quantum network need not be confined to the ground. The sky itself can carry the connection. There is a long way still to travel, from a single satellite demonstration to a functioning global quantum network. The technology is young, and the challenges are real. But the principle has been shown to hold at distances that matter. And somewhere in that fact, in the image of a satellite passing silently over a darkened continent, releasing pairs of entangled photons toward 2 distant telescopes below, there is something worth resting with for a moment. 2 particles, born together in a crystal aboard a machine in orbit, separated immediately, sent downward through hundreds of kilometers of open air, arriving at 2 different places on the surface of the Earth, and still, when measured, still correlated, still sharing that single, indivisible quantum state that no distance has managed to dissolve. The universe does not seem to mind how far apart they are. It never has. And yet the satellite itself is moving at roughly 7 kilometers per second. A low Earth orbit satellite does not hold still above its targets. It arcs across the sky in a matter of minutes. And every second of that arc introduces a small but measurable shift in the frequency of the photons it sends downward. This is the Doppler effect, the same gentle compression and stretching of waves that changes the pitch of a passing sound. At quantum scales, even a small frequency shift can disturb the delicate properties of an entangled photon. So the ground stations must account for it continuously, in real time, adjusting their receivers as the satellite moves, compensating for a shift that is always changing, always requiring correction. And then there is the atmosphere itself. The air between a satellite and the ground is not uniform. It moves in slow, invisible currents, in pockets of different temperature and density. Light passing through it bends slightly, scatters slightly, arrives at the telescope a little blurred. For ordinary communication, this is a minor inconvenience. For entangled photons, it is a more serious challenge, because the quantum state being carried is fragile in ways that a classical signal is not. Atmospheric turbulence does not destroy the entanglement outright, but it reduces the rate at which usable entangled pairs arrive at the detectors. It lowers the fidelity. It asks the engineers to work harder for every correlated pair they manage to collect. That these experiments succeed at all is a testament to how carefully the problem has been approached. But the sky is not the only path. Beneath the cities, beneath the streets and the buildings and the ordinary infrastructure of modern life, there are fiber optic cables, thin glass threads that carry light across continents, and researchers have been threading entangled photons through them too. Entanglement has now been maintained across fiber links of more than 100 kilometers in metropolitan quantum network demonstrations. 100 kilometers of glass, of bends and splices and connectors, and the correlation survives. It does not survive easily. Photons are absorbed by the fiber as they travel, and the longer the link, the fewer photons arrive. The entanglement fidelity tends to fall with distance, but within the range of a city, across the scale of an urban network, it has been shown to hold, and that is the scale that matters first, because cities are where the computers are, where the sensors are, where the people and institutions are that would first make use of a quantum network. The vision that researchers are working toward is something like this: a network of quantum devices, computers, sensors, clocks, communication nodes, connected to one another not by classical electrical signals, but by entanglement. The way the classical internet connects machines through the exchange of bits, a quantum network would connect them through the sharing of quantum states, through entangled pairs distributed across the links between nodes. Each connection would be a live quantum resource, not just a channel for information, but a physical bond between two distant systems. This is sometimes called the quantum internet. The phrase carries a certain weight because the classical internet changed so much about how knowledge moves and how work gets done. A quantum internet would not replace it. The two would exist alongside each other, serving different purposes. But for certain tasks, the quantum network would offer something the classical one simply cannot. One of those tasks is distributed quantum computing. A single quantum processor is limited by how many qubits it can hold and keep coherent. Scaling up is difficult. But if two quantum processors could share entangled qubits across a network link, they could in principle act as a single larger system, dividing a computation between them, coordinating their results through the entanglement that connects them. The physical machines could be in different buildings, different cities, and yet the quantum state they share would make them, in a meaningful sense, one. This is not yet a reality. The engineering challenges are substantial, and the field is still young. But the principle is sound, and the early demonstrations are pointing in the right direction. And then there is sensing. Entanglement is not only useful for computing and communication, it is also a tool for measurement, and in some ways, this may be where its near-term impact is felt most clearly. Classical measurements are limited by what physicists call the standard quantum limit, a boundary set by the uncertainty principle, beyond which ordinary measurement strategies cannot improve. Entanglement allows that boundary to be pushed. When particles are entangled and used together as a sensing system, their correlated behavior can reveal information about the world with a precision that no classical arrangement of the same particles could achieve. This is quantum sensing. It applies to time, to gravity, to magnetic fields, to acceleration, to any physical quantity that can be probed by a quantum system. The entangled particles act together, their correlations amplifying the signal while suppressing the noise, and the result is a measurement that is quieter, sharper, more precise than what came before. One of the most striking applications is in timekeeping. Atomic clocks are already among the most precise instruments ever built. A modern atomic clock loses or gains roughly 1 second over hundreds of millions of years. That precision underlies GPS navigation, financial transaction timestamps, the synchronization of global communication networks. It is already woven into the fabric of daily life in ways most people never notice. Entangled atomic clocks can do better still. When two atomic clocks are connected by entanglement, they can be synchronized with a precision that surpasses any classical method. The entanglement allows the two clocks to compare their states in a way that reduces the quantum noise in the comparison itself. The result is a shared timekeeping that is more stable, more accurate, more tightly bound between the two locations than anything achievable without it. The applications reach in several directions at once. For navigation, more precise time means more precise position. For fundamental physics, synchronized clocks at different locations on the Earth's surface could detect the tiny differences in the flow of time caused by differences in gravitational potential, a direct measurement of general relativity playing out across the landscape of a single planet. For deep space communication, entangled clocks could allow coordination between distant probes and ground stations with a fidelity that classical synchronization cannot match. These are not distant speculations. Some of them are being tested now. in laboratories, and in early field demonstrations. The technology is not yet mature, but the physics behind it is well understood, and the experiments are confirming what the theory predicts. There is something quietly remarkable about all of this. Entanglement was, for decades, primarily a philosophical puzzle, a strange feature of quantum mechanics that troubled its founders and resisted easy interpretation. Einstein found it troubling enough to argue that it implied the theory was incomplete. Schrödinger called it the defining trait of the whole framework and seemed uncertain whether that was a comfort or a concern. And now it is an engineering resource, something that can be generated in a crystal, transmitted through fiber or open air, stored briefly in a trapped ion, swapped through an intermediary, and put to work measuring the world more precisely than the world has ever been measured before. The strangeness has not gone away. The deep questions about what entanglement means, about what it says about the nature of space and connection and the structure of reality, those questions are still open. But alongside them, quietly and steadily, a technology has been growing, built on correlations that no one fully understands, doing work that nothing else can do. And all of it resting on that same simple, strange fact that two particles, once joined, carry something of each other forward, across whatever distance the world places between them. There is an instrument in the state of Louisiana and another in Washington state that can detect a change in length smaller than 1/10,000th the diameter of a proton. Each one is an L-shaped tunnel, 4 kilometers on each side, carved into the earth and held in near perfect vacuum. And when a gravitational wave passes through, a ripple in space-time itself, sent out by 2 colliding black holes a billion light years away, these tunnels stretch and compress by an amount almost too small to name. To measure that, you need light, carefully prepared, carefully aimed light, split and sent down both arms of the tunnel and brought back together to interfere. But light carries its own uncertainty. Even a perfectly controlled laser beam has quantum noise built into it, fluctuations in the number of photons arriving at the detector, fluctuations that blur the measurement and set a floor on how precisely anything can be read. This is the standard quantum limit, a boundary set not by the quality of the instrument, but by the nature of quantum mechanics itself. And yet, LIGO has found a way to push beneath it. The technique is called squeezed light. Quantum mechanics allows uncertainty to be redistributed between pairs of conjugate properties, properties that are linked by the same fundamental trade-off that governs position and momentum, or energy and time. In a beam of light, the relevant pair is phase and amplitude. The noise in one can be reduced, but only by allowing the noise in the other to grow. Squeezed light does exactly that. It takes the quantum uncertainty and reshapes it, compressing the fluctuations in the property being measured and letting them expand in the property that is not. The total uncertainty is conserved, as quantum mechanics requires. But the noise that matters, the noise that would otherwise blur the signal, has been pushed aside. What remains is a measurement more precise than the vacuum itself would ordinarily allow. There is something quietly remarkable about that. An instrument built to listen for the faintest tremors in the fabric of space-time, made more sensitive by deliberately distorting the shape of quantum noise. The universe sets limits, and then, within those limits, it offers room to maneuver. Entanglement has its own way of being measured. When two systems are entangled, physicists can ask how entangled they are, how deeply their fates are woven together, how much information about one is carried by the other. The answer is given by a quantity called entanglement entropy. It is borrowed from thermodynamics, from the older idea of entropy as a measure of disorder or missing information. But here it measures something more specific: the degree to which two subsystems share a quantum state that neither one possesses alone. If the entanglement entropy between two particles is zero, they are completely independent. Knowing everything about one tells you nothing about the other. If it is at its maximum value, the two are as deeply entangled as quantum mechanics allows. Every measurement on one is perfectly mirrored in the other, and neither particle has any definite state of its own. Between those extremes lies a continuous landscape of partial entanglement, partial correlation, partial shared fate. Entanglement entropy appears throughout quantum information theory. It governs how much quantum information can be transmitted through a channel, how efficiently a quantum state can be compressed, how much classical information is needed to describe a quantum system from the outside. It is, in a sense, the currency of quantum information, the thing that gets spent and transferred and carefully accounted for whenever quantum systems interact and compute and communicate. And computation is where entanglement becomes, perhaps, most visibly powerful. A classical computer works with bits. Each bit is either 0 or 1. A string of bits encodes a single number, and the computer processes that number one step at a time. A quantum computer works with qubits. Each qubit can exist in a superposition of 0 and 1 simultaneously. And when qubits are entangled, their joint state is not just a collection of individual superpositions, it is something richer, something that cannot be broken apart into independent pieces. Two entangled qubits do not simply hold two superpositions. They hold a superposition of all four possible combinations of their values at once. 3 entangled qubits hold 8, 10 hold 1,000. 300 entangled qubits hold more simultaneous states than there are atoms in the observable universe. A quantum processor, operating on all of those states at once, can explore a vast landscape of computational possibilities in a single operation. This is not magic, and it is not quite the same as running many calculations in parallel in the classical sense. The art of quantum computing lies in designing algorithms that guide this exploration, that use interference to amplify the paths leading toward the right answer, and cancel out the paths that lead away from it. Entanglement is what makes the exploration coherent, what keeps the qubits from simply collapsing into independent, unrelated superpositions, what allows the interference to be structured and purposeful rather than random. One of the clearest demonstrations of what this makes possible is an algorithm for factoring large numbers. Factoring, finding the two prime numbers that multiply together to produce a given large number, is believed to be genuinely hard for classical computers, hard in a precise mathematical sense. The time required grows so quickly with the size of the number that factoring a sufficiently large one would take longer than the current age of the universe, even on the fastest machines available. This hardness is the foundation of most modern cryptography. The security of encrypted communications rests on the assumption that factoring is practically impossible at scale. In 1994, a mathematician named Peter Shor described an algorithm that could factor large numbers on a quantum computer in a time that grows only polynomially with the size of the input, exponentially faster than the best-known classical approach. Shor's algorithm works by transforming the factoring problem into a question about periodicity, about finding a repeating pattern in a mathematical function. Quantum interference, guided by entanglement, allows the period to be found with remarkable efficiency. The algorithm has been demonstrated experimentally on small numbers. The quantum hardware capable of running it at cryptographically relevant scales does not yet exist. But the theoretical result is exact, and the implications are clear. Entanglement, in the right hands, can dissolve a problem that classical computation cannot touch. There is a quieter example, less dramatic, but no less precise. Searching an unsorted list for a specific item is classically a problem of patience. If the list has 1,000,000 entries, you may need to check, on average, 500,000 of them before finding what you want. An algorithm described by Love Grover in 1996 uses entanglement and quantum interference to search the same list in roughly 1,000 steps, the square root of 1,000,000. The speedup is quadratic rather than exponential, more modest than Shor's result, but provably optimal. No quantum algorithm can do better for this class of problem, and no classical algorithm can match it. Grover's algorithm is a reminder that quantum advantage does not always arrive as a sudden, overwhelming leap. Sometimes it is a steady, structural improvement, a quieter kind of power, built into the geometry of how quantum states explore possibility. All of this, the squeezed light, the entanglement entropy, the algorithms that reshape what computation can mean, rests on the same foundation. Two particles, joined, their states inseparable, their outcomes correlated across whatever distance the world places between them. From that single strange fact, an entire architecture of possibility has been built. Quietly, carefully, one experiment at a time. And yet, from that foundation, the work continued. Researchers did not stop at algorithms run on paper or on small systems of a handful of qubits. They wanted to know whether a real machine, built from real entangled particles, subject to real noise and imperfection, could do something a classical computer genuinely could not. The answer, as far as we can tell, is yes. In recent years, quantum processors using entangled arrays of superconducting qubits have performed specific computational tasks that would take the most powerful classical supercomputers an impractical length of time to reproduce. The tasks themselves are narrow, carefully chosen to sit in the region where quantum systems have a natural advantage. They're not general-purpose calculations. They're more like a proof of principle, a demonstration that the territory exists. But the territory is real. This is what physicists mean by quantum supremacy. Not that quantum computers have surpassed classical ones in every way, but that a threshold has been crossed, a point where entanglement, operating across dozens of qubits simultaneously, produces something a classical machine cannot efficiently simulate. The correlations become too deep, too numerous, too intricately woven for any classical description to keep pace. And the deeper you look into the structure of entanglement, the stranger it becomes. Most of what has been described so far involves pairs, two particles, joined, but entanglement does not stop at two. In 1989, Daniel Greenberger, Michael Horn, and Anton Zeilinger described a state involving three particles entangled together in a way that goes beyond anything a pair can demonstrate. The state that bears their names, the GHZ state, is not simply a larger version of a Bell pair. It is qualitatively different. A Bell pair violates local realism statistically. You run many measurements, accumulate the results, and the numbers exceed what any hidden variable theory permits. The violation emerges from the pattern. A G-gate state does something more direct. Measure the three particles in the right way, just once, and the outcome is already impossible under any local hidden variable theory. Not improbable, impossible. A single round of measurement is enough to rule out the entire class of theories that Einstein's intuition pointed toward. No statistics required. No accumulation of evidence over many trials. It is as though the universe, when asked directly, simply refuses to pretend. The GHZ state has been realized experimentally, in photons, in trapped ions, in superconducting circuits, and each time, the result is the same. Local realism does not survive contact with three entangled particles measured together. There is something quietly final about that. And yet the story of multi-particle entanglement does not end with three. Physicists have constructed entangled states involving dozens, and in some cases hundreds, of particles. Some of these states are built not to demonstrate a philosophical point, but to serve as a resource, a kind of raw material from which computation can be drawn. These are called cluster states. A cluster state is a large collection of particles, each entangled with its neighbors in a carefully arranged pattern. The entanglement is not between one pair or one trio, but woven through the entire structure like a lattice. Every particle connected to those around it, the whole thing holding a kind of distributed quantum information that no single particle contains alone. What makes cluster states remarkable is what you can do with them. In ordinary quantum computing, you manipulate qubits by applying sequences of operations, gates, that transform their states step by step. In measurement-based quantum computing, you do something different. You begin with the cluster state already prepared, and then you simply measure the particles, one by one, in a chosen order and orientation. The act of measuring is the computation. Each measurement collapses one particle out of the entangled structure, and in doing so, it shapes what remains. The information flows through the cluster as measurements proceed, guided by the choices made at each step. By the end, the final unmeasured particles hold the result. It is a strange inversion of the usual picture. In classical computing, you preserve information and transform it. Here, you consume the entanglement particle by particle, and the consumption itself is the process. The cluster state is used up, but the answer remains. This approach has practical advantages in certain physical systems, where preparing entanglement in advance is easier than applying precise gate operations in real time. It also offers a different way of thinking about what computation is, not a sequence of transformations, but a pattern of observations, each one narrowing the quantum possibilities until only the answer is left. All of this, the supremacy experiments, the GHZ states, the cluster states, and their measurement-based architectures, rests on entanglement as a resource. Something that can be created, structured, and spent. But there is a constraint on that resource that shapes everything. Entanglement is not freely shareable. This is one of the deeper principles in quantum information theory, and it goes by the name of monogamy. If two particles are maximally entangled with each other, as perfectly correlated as quantum mechanics allows, then neither of them can be entangled with anything else. Not partially, not at all. Entanglement, at its maximum, is exclusive. This is not a technological limitation. It is not something that better engineering might one day overcome. It is a mathematical fact built into the structure of quantum states. The more strongly particle A is entangled with particle B, the less entanglement either of them can share with a third particle C. The relationship is zero-sum, in a precise and provable sense. At first, this might seem like a restriction, a ceiling on how richly entangled a system can become, and in some ways it is, but it is also a gift. Monogamy of entanglement is the reason quantum cryptography works. When two parties share a maximally entangled pair and use it to generate a secret key, the monogamy principle guarantees that no third party can hold any entanglement with those particles. An eavesdropper cannot be silently woven into the correlation. Any attempt to intercept or copy the entangled state necessarily disturbs it, because the eavesdropper cannot share in the entanglement without displacing one of the original parties. The security is not enforced by computational difficulty, the way classical cryptography often is. It is enforced by the geometry of quantum states themselves, by the simple fact that a particle fully committed to one partner has nothing left to give. There is something almost tender in that. Two particles, maximally entangled, holding a correlation that cannot be diluted, cannot be copied, cannot be shared without being broken. Their connection is, in a precise mathematical sense, complete. And this completeness, this monogamy, ripples outward into every application built on entanglement, into the security of quantum networks, into the architecture of quantum error correction, into the careful accounting of entanglement entropy that tells researchers how much of this resource remains in a system and how much has been lost to the environment. Entanglement is not infinite. It is not free. It obeys rules. But within those rules, it enables things that nothing else in nature permits. A correlation that holds across any distance. A computation that proceeds by consumption rather than transformation. A security guarantee written not in code, but in the laws of physics. All of it resting on the same quiet strangeness that Schrödinger named in 1935, that Einstein doubted, that Bell made testable, and that a long succession of careful experimenters confirmed, one loophole at a time. Two particles, joined. Their fates intertwined in a way that space cannot undo. Rest in that for a moment. And that monogamy, that fundamental limit on how entanglement can be shared, is not merely a curiosity of quantum mechanics. It is a guarantee. When two parties share a maximally entangled pair, the laws of physics themselves ensure that no third party can hold any portion of that same entanglement. An eavesdropper cannot quietly siphon off a copy. They cannot intercept the correlation without disturbing it. The security of quantum cryptography does not rest on the difficulty of a mathematical problem. The way classical encryption does, it rests on something deeper, on the structure of quantum states themselves, on the fact that entanglement, once fully given, cannot be given again. This is what makes quantum key distribution different from anything that came before it. Not faster, not more convenient, fundamentally different in kind. And yet, for all its practical power, entanglement has also led physicists somewhere, far stranger than any laboratory, into questions about the nature of space itself. There is a conjecture in theoretical physics, still debated, still being explored, that suggests entanglement may not merely exist within space-time, but may be part of what creates it. The holographic principle, developed through work on black holes and string theory, proposes that the information content of a region of space can be fully described by what lies on its boundary, like a three-dimensional room whose entire contents are encoded on its two-dimensional walls. It is a strange idea, and it leads somewhere stranger still. When physicists began studying the entanglement structure of quantum fields, the way different regions of a quantum system are correlated with one another, they found that this structure seemed to mirror the geometry of the space those fields inhabit. The more entangled two regions were, the closer they appeared to be in the emergent geometry. The less entangled, the more distant. As if distance itself were a measure of how much two regions share. As if space were woven from correlation. This is not yet a proven theory. It is a direction. A set of mathematical hints pointing somewhere that physicists are still learning to read. But the hints are consistent enough that many researchers take them seriously. And they lead to one of the most quietly astonishing conjectures in modern physics. In 2013, Juan Maldacena and Leonard Susskind proposed what has come to be called ER equals EPR. ER refers to the Einstein-Rosen bridge, a wormhole, a tunnel through spacetime connecting two distant regions. EPR refers to the Einstein-Podolsky-Rosen paper, and by extension, to entanglement itself. The conjecture proposes that these two things, a wormhole and an entangled pair, are not merely analogous. They may be the same thing, described in two different languages. An entangled pair of particles In this view is a wormhole. Microscopic, non-traversable, carrying no matter and no signal. But geometrically real, a thread of space-time connecting two points that are otherwise far apart. Rest with that for a moment. Two particles, entangled in a laboratory, may be connected not just by correlation, but by geometry, by a tiny fold in the fabric of space itself. This is speculative. It is the frontier of theoretical physics, not settled science. But it is the kind of speculation that emerges from deep mathematical consistency, not from imagination alone. And it changes how one thinks about what entanglement is. Not a strange feature of small things. Perhaps a structural feature of everything. Nowhere does this become more vivid or more troubling than at the edge of a black hole. A black hole is a region of space-time where gravity has become so strong that nothing, not even light, can escape past the boundary called the event horizon. What happens at that boundary, and just beyond it, is one of the deepest unsolved problems in physics. Entanglement is at the center of it. When a black hole forms and begins to slowly radiate through the process Stephen Hawking described in 1974, the radiation it emits is thought to be entangled with the interior of the black hole. Each particle that escapes carries a quantum correlation with something left behind. Over time, as the black hole slowly evaporates, a question arises that has no clean answer. What happens to the information encoded in everything that fell in? Quantum mechanics insists that information cannot be destroyed, that the complete description of a physical system must be preserved, even as the system evolves. But if a black hole evaporates entirely, and the radiation it leaves behind is thermal, random, featureless, then the information seems to be gone. This is the black hole information paradox, and entanglement makes it sharper. As the black hole grows older and more than half of it has evaporated, the remaining radiation outside must, by the rules of quantum mechanics, become increasingly entangled with the early radiation already emitted. But it is also supposed to be entangled with the interior, and monogamy of entanglement says it cannot be both. Not fully, not without contradiction. This tension led to the firewall proposal. The suggestion that the event horizon might not be the quiet, unremarkable boundary that general relativity describes, but a surface of intense energy, a wall of radiation, where the entanglement structure breaks down. Whether firewalls exist, whether information escapes in the radiation, whether the ER equals EPR conjecture resolves the paradox, these questions remain open, carefully, seriously open. Among the most active areas of theoretical physics today. And they all trace back to the same quiet property. That two particles, once entangled, share something that space cannot separate. From the largest scales of theoretical physics, let the mind drift now towards something smaller, something alive. There is a question that has been asked, carefully and with appropriate uncertainty, about whether entanglement plays a role not just in laboratories and black holes, but in living things. Photosynthesis, the process by which plants and certain bacteria convert light into chemical energy, is extraordinarily efficient, more efficient, in some respects, than classical physics alone would easily explain. In the early stages of photosynthesis, energy absorbed from a photon must travel through a network of molecules to reach the reaction center where it can be stored. And for a time, researchers observed that this transfer seemed to occur with a coherence, a wave-like quality, that suggested quantum effects might be involved. Some proposed that entanglement, or at least quantum superposition, might allow the energy to explore multiple pathways simultaneously, finding the most efficient route the way a quantum system can. The evidence, however, remains contested. Later experiments suggested that some of the observed coherence might be explained by classical vibrations in the molecular environment, rather than by genuine quantum entanglement. The question has not been closed. It has been made more careful, more nuanced. The honest answer, as of now, is that quantum effects may play some role in biological energy transfer, but the extent and nature of that role is still being worked out. There is also the question of bird navigation. Certain migratory birds appear to sense the Earth's magnetic field with remarkable precision. One proposed mechanism involves a protein called cryptochrome, found in the eye, where light triggers the formation of a pair of molecules with unpaired electrons, a radical pair, whose quantum spin states may be entangled. The orientation of the magnetic field would then influence how those spin states evolve, and ultimately, what chemical signal the bird receives. It is a delicate idea, and like the photosynthesis question, it remains under active investigation. The evidence is suggestive, but not conclusive. The experiments are difficult. The systems are warm and wet and complex, which is precisely the environment where quantum coherence is hardest to maintain. But the possibility is real enough to study seriously, and there is something quietly moving about it. That the same phenomenon described by Schrödinger in 1935, tested in cold, isolated laboratories, debated by physicists for decades, might also be at work in the eye of a small bird, finding its way home across a darkened sky. And perhaps that is enough, for now, to hold the possibility gently, without needing to resolve it. Science moves slowly when the questions are hard, and the hardest questions tend to be the ones that matter most. Whether entanglement plays a role in living systems, in the chemistry of a bird's eye, in the machinery of a leaf, remains open. The honest answer is that we do not yet know, and that not knowing is not a failure. It is simply where the work is still being done. There are other open questions, deeper ones, that have resisted resolution for much longer. One of them sits at the very heart of quantum mechanics itself. It is called the measurement problem. And it goes something like this. A particle, before it is measured, exists in superposition, spread across multiple possible states at once. Not because we are ignorant of which state it is in, but because, as far as the mathematics tells us, it genuinely has no single definite state yet. Then a measurement happens, and suddenly there is one outcome, one definite value. The superposition is gone. The question is, why? What is it about measurement that causes this collapse? What counts as a measurement? Is it the detector? Is it the observer? Is it something about the interaction between a quantum system and a large classical one? No one fully agrees. There are interpretations, many of them, each internally consistent, each with its own picture of what is really happening. The Copenhagen interpretation says the wave function collapses upon measurement, and that asking what happens before measurement is simply not a meaningful question. The many-worlds interpretation says the wave function never collapses at all. Every outcome occurs in branching versions of reality that never interact again. Pilot wave theories say particles always have definite positions, guided by a wave that carries the quantum information. Relational interpretations say quantum states are not absolute, but defined only relative to other systems. Each of these is a serious proposal, held by serious physicists. None of them is universally accepted. The measurement problem has been with us since the earliest days of quantum theory, and it remains, quietly, one of the deepest unresolved questions in all of physics. It is not a gap that will be filled by a slightly better experiment. It touches something more fundamental, what it means for something to be real, what it means for something to happen, what the relationship is between the mathematical structure of quantum mechanics and the world we actually experience. These are not small questions, and they are still open. But even without resolving them, quantum mechanics works. It predicts, with extraordinary precision, what experiments will find. The formalism is not in doubt, only the interpretation, the story we tell about what the formalism means, remains unsettled. And entanglement sits right at the center of that unsettledness. Because entanglement is where the strangeness is most concentrated, where the gap between the mathematics and our intuitions is widest. Two particles, one, quantum state, no definite properties until measurement, and then, when one is measured, the other responds, not because a signal traveled between them, but because they were never truly separate to begin with. And here is something worth resting with as you lie in the quiet. Entanglement does not care about distance. The correlations it produces are exactly the same whether the two particles are a few centimeters apart on a laboratory bench or separated by the width of a city, or, in principle, by the span of a galaxy. There is no fading with distance, no weakening as the space between them grows. The connection does not thin out the way sound does, or light does, or any influence that travels through a medium. It simply is the same, wherever the particles are. This is not a poetic exaggeration. It is what the experiments show and what the mathematics predicts. Bell's inequality is violated just as strongly at 1,000 kilometers as it is at a meter. The geometry of space does not dilute the correlation. In some sense, entangled particles do not experience the distance between them the way ordinary objects do. The space that separates them is, in some deep way, not relevant to what they share. Physicists are still working out what that means. Some of the most speculative and beautiful ideas in theoretical physics, the holographic principle, the ER equals EPR conjecture, suggest that entanglement and the structure of space may be more intimately related than we ever suspected. That perhaps the geometry of the universe, the very fabric of space and time, is in some way woven from the entanglement of quantum fields. These are ideas at the frontier, not established facts, but serious proposals being seriously explored, and they suggest that entanglement is not merely a curiosity at the edge of physics. It may be something closer to the foundation. For now, though, let the distance go. Let the image be simple. Two particles, created together in a moment of interaction, sent out into the world in different directions, perhaps carried by light, perhaps held in the cold stillness of a trapped ion, perhaps traveling through fiber beneath a city or through the open air between a satellite and the ground. And wherever they end up, however far apart, they remain, in some sense, one thing. Not connected by a wire, not linked by a signal, not held together by any force that diminishes with distance. Just correlated, in a way that has no classical explanation and no classical equivalent. Every entangled pair ever created carries this quality. Every pair produced in a laboratory, in a crystal, in the heart of an experiment designed to test the limits of what nature allows. Every pair sent through fiber, or through open sky, or used to generate a cryptographic key, or to teleport a quantum state, or to probe the behavior of a quantum computer. Each one is a small, quiet demonstration of something the universe seems to have built into itself from the beginning. That there are connections here, real, physical connections, that do not diminish with distance, that do not require a medium to cross the space between, that hold, across whatever separation the world places between two things that were once, briefly, one. There is no need to make more of this than it is. The universe is not sending messages. Entanglement does not mean that everything is secretly unified in some mystical sense. The physics is precise, and the physics is enough. But the physics, taken on its own terms, is already something worth sitting with in the dark. That two particles, born from a single interaction, carry a shared fate across any distance. That the correlations between them are not written in advance, not carried like hidden instructions, but genuinely undetermined until the moment of measurement. And then, in that moment, resolved together, as if the distance between them were nothing at all. The universe, it turns out, holds connections that space cannot sever. And that is not a metaphor. It is simply what the experiments show. Quietly, and without exception, every time. And so we rest here, for a moment, with what the experiments have already given us. Before moving further into what entanglement makes possible, the technologies, the questions it opens at the edges of physics, it is worth pausing on something quieter. The fact that this is real, not a theory waiting to be overturned, not a philosophical position, but a measured, repeatable feature of the physical world. Particles entangled in a laboratory, separated by distance, and found, every time, without exception, to be correlated in ways that no classical explanation can account for. That is where we are. And from that ground, something remarkable has been built. Entanglement is not only a curiosity, it is, in the language of physics, a resource, something that can be created, carefully preserved, distributed across space, and put to use. The way a battery stores energy, an entangled pair stores a kind of quantum relationship, one that can be drawn upon. One of the most striking uses of that resource is something called quantum teleportation. The name is dramatic, and the reality is quieter than the name suggests, but no less remarkable for that. Quantum teleportation does not move matter, it moves information. The complete quantum state of a particle, everything that can be known about it, transferred to a distant location, without the particle itself making the journey. It requires an entangled pair shared between two locations, and it requires a classical channel alongside it, an ordinary signal, traveling at ordinary speeds, so nothing exceeds the speed of light. The no communication theorem holds, as it always does. But the quantum state arrives whole, at the far end, reconstructed perfectly. Anton Zeilinger's group demonstrated this with a photon in 1997, in Innsbruck, a quiet experiment, in a quiet laboratory that transferred something the universe had said could not be copied, could not be intercepted without disturbance, across space, intact. That same fragility is what makes entanglement so valuable for cryptography. If two parties share an entangled pair, and an eavesdropper intercepts one of the photons, the quantum state is disturbed. The disturbance is detectable. The eavesdropper cannot listen in silently. The physics does not allow it. And so a key built from entangled particles carries its own proof of privacy, written into the correlations themselves. This is not a matter of computational difficulty. The way classical encryption is, it is a matter of physical law. The Eckert protocol uses Bell inequality violations directly as the security guarantee. If the correlations are strong enough to violate Bell's inequality, no third party has touched the particles. The key is clean. The channel is private, not by assumption, but by measurement. Entanglement has now traveled through fiber links stretching over 100 kilometers. It has been distributed from orbit. In 2017, China's Miasis satellite sent entangled photon pairs between ground stations separated by 1,200 kilometers, through open air, through the atmosphere's turbulence, across the curve of the Earth. The engineering required for that is considerable. compensating for the motion of a satellite, for the shifting and bending of light through air, for the Doppler effect of something moving fast overhead. And yet, the entanglement arrived. The correlations held. Researchers are now working toward quantum networks, systems that would connect quantum processors and sensors the way classical networks connect ordinary computers, not with signals, but with entanglement. Shared quantum states, distributed across cities, across continents, eventually, perhaps further. Entanglement swapping makes this possible over long distances. Two particles that have never met can become entangled if each is entangled with a third particle that acts as an intermediary. The intermediary is measured, and the entanglement transfers, jumps, in a sense, to the outer pair. This is the mechanism behind quantum repeaters, which extend entanglement further than any single fiber link could carry it. A quantum internet, built from these pieces, would allow things classical networks cannot: distributed quantum computation, where entangled nodes share the work of a calculation across physical space. Quantum sensors network together, measuring the world with a precision that classical instruments cannot reach. Entangled atomic clocks, for instance, can synchronize more precisely than any classical method allows. The implications reach into navigation, into tests of fundamental physics, into the measurement of time itself at its finest resolution. And then there is sensing of a different kind. The LIGO detector, the instrument that first heard gravitational waves, the faint ripple of two black holes merging over 1 billion years ago, uses a technique called squeezed light to push its sensitivity below what ordinary quantum mechanics would permit. Squeezed light redistributes quantum uncertainty. It reduces noise in one measured property by accepting more noise in another. A careful trade, made possible by the same quantum relationships that underlie entanglement. The universe's own geometry, detected through a quantum trick. In computing, entanglement does something different again. It allows a quantum processor to hold many possible states at once and to let them interfere with each other, amplifying correct answers, canceling wrong ones. Shor's algorithm uses this to factor large numbers exponentially faster than any classical machine. Grover's algorithm uses it to search through possibilities with a speed no classical approach can match. These are not small improvements. They represent a different relationship between computation and time. And the entangled states involved grow more intricate as the systems grow larger. The GHZ state, named for Greenberger, Horn, and Zeilinger, entangles 3 particles in a configuration that rules out local hidden variables, not through statistical accumulation, but in a single measurement round. One experiment, and the classical picture is gone. Cluster states go further still, large, carefully woven arrangements of entangled particles that serve as the substrate for an entire style of quantum computing, where the computation itself proceeds through measurement, step by step, each measurement guiding the next. There is also a principle called entanglement monogamy. A particle that is maximally entangled with one partner cannot be entangled with any other. The quantum relationship is exclusive. In a precise mathematical sense, this is not a poetic observation. It is a theorem, and it is what makes quantum cryptography secure at its foundation. A key shared between 2 parties cannot simultaneously be shared with a third. The physics forbids it. And then, at the furthest edges of what physicists are currently thinking about, entanglement appears again, in places that feel very far from any laboratory. There is a conjecture, still debated, still being worked through, that connects entanglement to the geometry of space-time itself. The holographic principle suggests that the entanglement structure of quantum fields may be what gives rise to the shape of space. That geometry, in some deep sense, is woven from quantum correlations. A related idea, sometimes written as ER equals EPR, proposes that an entangled particle pair is geometrically equivalent to a wormhole, a connection through spacetime, not across it. The two descriptions, it is suggested, may be the same description seen from different angles. These ideas are speculative. They are the frontier, not the settled ground. But they point towards something that the experiments, in their quiet way, have been suggesting all along. That entanglement is not a peripheral feature of quantum mechanics. It is, as Schrödinger said in 1935, the defining trait, the thing that makes quantum mechanics what it is, and not something else. Even in biology, the question has been raised whether entanglement plays a role in photosynthesis, in the way some birds may sense the Earth's magnetic field through chemical reactions in their eyes. The evidence is contested, the question carefully open. But the fact that it is being asked at all says something about how far this thread has been followed. Entanglement does not privilege any location in space. The correlations it produces are the same whether the particles are centimeters apart or light years apart. Distance, in this one precise sense, does not matter. And that remains, even after everything that has been built upon it, a quiet and extraordinary thing to know about the world. And yet, there is something that does not resolve, even after the experiments, even after the theorems and the satellites and the Nobel lectures. Something that sits quietly at the center of all of it and does not move. The measurement problem. When a particle exists in superposition, genuinely, mathematically in multiple states at once, and then a measurement is made, something happens. The superposition ends. One outcome appears, the others do not. And no one, as far as we can tell, fully understands why. This is not a gap waiting to be filled by a slightly better instrument. It is a conceptual gap, a place where the formalism of quantum mechanics stops short of telling us what is actually happening in the world. The equation that governs how quantum states evolve is smooth and continuous and perfectly reversible. It does not contain us. Anywhere within it, the sudden jump from many possibilities to one, and yet the jump happens. Every time. There are interpretations, many of them. Each one takes the mathematics seriously and tries to build a picture of reality around it. Some say the other outcomes still occur, branching silently into worlds we cannot access. Some say the wave function is not a description of reality, but only of our knowledge, and the jump is simply an update. Some say there is a physical process, not yet understood, that causes the collapse. None of these interpretations can currently be distinguished by experiment. They make the same predictions. They simply disagree, quietly and irreconcilably, about what is real. Entanglement sits at the heart of this, because when two particles are entangled and one is measured, something about the other is instantly settled, across whatever distance separates them. And the question of what that settling means, whether it is a change in the world or only a change in what we know about the world, is exactly the question the measurement problem is asking. It has been asking it since 1935. It is still asking. And there is something almost restful in that, a question so deep it has outlasted every attempt to dissolve it, remaining open not from neglect, but from genuine difficulty. The universe, it seems, does not give up its deepest answers easily, or perhaps at all. What we do have is this: two particles created together, or brought into contact, or linked through an intermediary they each touched in turn, and from that moment, something holds between them. Not a force, not a signal, not a thread of any kind that physics has a name for, but a correlation that no distance weakens, and no classical explanation accounts for. Bell showed it could be tested. Clauser tested it. Aspect refined it. Zeilinger extended it across cities, across open air, eventually to a satellite moving through low orbit above the Earth, distributing entanglement to stations more than 1,000 kilometers apart. And at every scale, the correlations held. Stronger than any hidden instruction set could produce, stronger than anything locally realistic. The universe, in this one precise and measurable sense, is not locally realistic. That sentence is worth sitting with for a moment. Not locally realistic. Either something influences something else across space without traveling through it, or the outcomes were never determined until the moment of measurement, or reality is somehow larger than the single branch of it we find ourselves in. All three possibilities are strange. All three have serious defenders. And the experiments do not choose between them. They only confirm, again and again, that the correlations are real. That entanglement is real. That whatever it is not nothing. There is a principle called monogamy of entanglement. A particle that is maximally entangled with one partner cannot be entangled with another. The connection, whatever it is exclusive in this precise mathematical sense. It cannot be shared without being diluted. This is what makes quantum cryptography secure at its foundations. A key woven from entanglement cannot be intercepted without disturbing it, cannot be copied without leaving a trace. The eavesdropper is not defeated by clever engineering alone, but by the structure of quantum mechanics itself. By monogamy. By the fact that entanglement, once fully committed, has nothing left to give a third party. There is something almost tender in that. A connection that cannot be shared without being broken. And then there is the other direction. Not the intimate scale of two particles, but the largest scales physics can reach. The holographic principle suggests that the entanglement structure of quantum fields, the web of correlations threading through space, may be what gives rise to the geometry of space-time itself. That space, as we experience it, as we move through it, as we measure distances across it, may be in some sense woven from entanglement. This is speculative. It is theoretical physics at its most exploratory, but it is taken seriously, and it connects to the conjecture that an entangled pair of particles may be, in some deep geometric sense, equivalent to a wormhole. Two regions of space-time connected not by a tunnel through space, but by the entanglement between them. The same connection. Described two ways. If this is right, and it may not be, it is a frontier, not a conclusion. Then entanglement is not merely a feature of quantum mechanics. It is part of the architecture of the universe, part of what holds the geometry of space together, part of what makes here and there mean anything at all. That thought can rest here without being resolved. It does not need to be resolved tonight. What Schrödinger called the defining trait of quantum mechanics in 1935 has turned out to be a resource, a tool, a security guarantee, a bridge between nodes in a quantum network, a component of algorithms that factor numbers in search databases and perform computations no classical machine can replicate in any reasonable span of time. It has been sent to space. It has been threaded through fiber beneath cities. It has been preserved in the stillness of trapped ions for seconds at a time, which in the quantum world is a very long time. And it has raised questions that reach from the behavior of electrons to the nature of black holes, to the possibility that birds navigate by sensing the Earth's magnetic field through quantum chemistry in their eyes. All of this from a correlation. From two particles that touched, or were born together, and carried something of that contact forward. regardless of what came after. Regardless of distance, the universe holds connections that do not diminish, that do not require a medium, that do not ask permission from the space between. And somewhere, in a laboratory that is probably cold and quiet at this hour, two photons are being born from a single photon passing through a crystal, emerging in two directions, carrying between them a correlation that has no classical name. They will travel a short distance. They will be measured. The correlation will hold, as it always does, as it has in every experiment since the first one, and then they will be gone, and two more will take their place, quietly, without ceremony. The universe making its connections in the dark.